Hey guys, so we are starting our next unit. So this is lesson 8A, which is about hypothesis tests. So we're going to go ahead and get started. Today we're going to conduct and interpret the results of a hypothesis test for a population proportion, and then we're going to talk about what a p-value is in context of a given situation. So in a hypothesis test, we talked about this during in-class, or if you watch the in-class video. So in a hypothesis test, our main kind of goal is to determine, could this observed occurrence, this thing that we saw that happened in our sample, be the result of chance variation? Meaning, is that just kind of like, that's what happens when we take random samples. Sometimes they're a little bit off from what's true. Or is that occurrence so unlikely to happen that it makes us have doubts? And as we talked about in class, right, our doubts could be about our initial assumption. Maybe our initial assumption about what was true about the population is off. Maybe it's one of our assumptions or conditions that we check that's slightly off, etc. So we're going to go ahead and jump into a problem, and I'm going to talk through the steps of how we do a hypothesis test in the context of this problem. So it is believed that a sampling bowl in an AP statistics classroom filled with red and white beads has 21% red beads in it. However, it is possible that someone has tampered with the bowl and added more white beads to the bowl, thus making the overall proportion of red beads less than 21%. To test the theory, a concerned student takes a random sample of 100 beads and finds that 14 of them are red. And we want to find, does the sample provide evidence that the bowl now has a lower percentage of red beads? So one thing I wanted to point out here, and this is where a hypothesis test comes in and what makes it a worthwhile problem to pursue, is that obviously 14 out of 100 is 14%. But remember, that's a sample. That's one sample of 100 beads out of this large sampling bowl that has thousands of beads in it, perhaps. So that one sample is not necessarily going to be a perfect, exact representation of the true percentage of red beads. So our goal is to find out, is this random sample where we got 14 out of 100 red beads, is that like so unlikely to happen that we would question the 21%, or is that just part of kind of that chance variation? So our 4 steps, if you remember from our class video or from class, for a hypothesis test is 4 things. We're going to state our hypotheses, we're going to check our assumptions and conditions, we're going to calculate our probability, find out how likely is it for this thing to happen, and then we're going to write a conclusion based on that probability. So let's start with step 1, which is writing hypothesis statements. So there's going to be 2 hypothesis statements that we write. The first one is called the null hypothesis, or it's kind of the initial thought process. It's a statement of there was no effect, no difference, no change. This value could reflect what used to be true or what is claimed to be true. And we use an equal sign to write that out. So we write H0, H with a little 0 subscript, that means null, means our initial starting assumption or hypothesis. And then we write P, because we're talking about a proportion, P equals and then a number. So whatever proportion we thought was true at the beginning of the problem, whatever was claimed to be true, we're using that equal sign and saying P equals that number. The other hypothesis that we write is called the alternative hypothesis or alternate hypothesis. And this is what we suspect is true or what we're trying to show is true. The value that we use, the actual number, should be the same as in the null hypothesis, but we're going to switch it. Instead of using an equal sign, we're going to use either a greater, a less than, or not equal to. And that's just based on what the claim or what the suspicion is. Do we think it's greater or less or not equal to that original number? And then one note that I wanted to make at the bottom here is that there's kind of 2 different ways you could write hypotheses. If you're going to write them using this P, you do have to define what P is before you write that. If you're going to use P in the hypothesis statement, you need to define P. The other option is just to write the entire hypothesis in words. And I'll show you what I mean on our example. So on our example, we are talking about the proportion of red beads that are in the bowl. That's kind of our goal in figuring out. So if I'm going to write my hypothesis that first way, my first step is to write out what is P. So P is the proportion of all the beads in the bowl that are red, or the true proportion of red beads in the bowl. Right, so then my null hypothesis, what used to be true, what is claimed to be true, was that there were 21% red beads. So my null hypothesis would be that P equals 0.21. So I would write H, the little 0 subscript, or just an O, is P equals 0.21. My alternative hypothesis, what I think might be true, what I'm trying to test, is I think that there are less than 21% now. I think someone came in and put some more white beads in there, and now there's less than 21% red beads. So my alternate hypothesis would be that P is less than 0.21. So those are my hypothesis statements. Again, we do have to define P if you're going to use P in your hypothesis statement. The other option would be to write the whole thing out in words. So H0, the null hypothesis, would be that the proportion of red beads in the bowl is 0.21. And then our alternate would be the proportion of red beads in the bowl is less than 0.21. So if I'm writing the whole thing out in words, that works too. But in sum, basically we need context is what it comes down to. So that's our first step, is to write our hypothesis statements. Our second step is to check our assumptions or conditions. So again, it's those same three conditions that we used when we talked about sampling distributions. We either assume or we're given a random sample. We assume or are given that the sample is less than 10% of the population. Just as a reminder, this is only necessary to check when sampling without replacement because that's what it's dealing with. And then our third is our check for normality, or the success failure condition. And that's where we check, does n times p and n times q come out to greater than or equal to 10? One little note I will make here, we should be using p from our null hypothesis to check this condition. Because the whole point of a hypothesis test is that we are assuming the null is true throughout this entire process. And then the probability we get is going to kind of help us determine, do we have evidence that the null is actually true or not? So just a little side note. So if the conditions are satisfied, we can use the normal model to conduct what we call a one proportion z-test, meaning that we're dealing with one proportion from one sample, and we're going to use a z-score to run a hypothesis test. Let's go back to our example and do our conditions assumptions. So our first assumption is that we have a random sample, and we were told that it was a random sample of 100 beads, so we can say given a random sample of 100 beads. Our second assumption is that the 10% rule passes. Since we are taking the sample without replacement, we need to assume that 100 is less than 10% of all the beads in the bowl. In other words, we need to assume that there are at least 1,000 beads in the bowl. And you could say it that way too. And then our last one is to check the NP and Q greater than 10. So for that one, N times P would be 100 times 0.21. Remember, 0.21 is our P from our null hypothesis, which is 21. And then N times Q would be 100 times 0.79. 1 minus 0.21 is 0.79. 79. Both of those are greater than 10. So a normal model may be used for our one proportion z-test. Our third step is to calculate the probability. So this is where we're using basically the same process as what we did with a sampling distribution problem. We're basically finding what is the probability of getting a sample of 14 out of 100 red beads if that 21% red beads in the entire bowl were actually true. So we're using a sampling distribution. So we kind of have to imagine we've got this normal model we've just determined based on our conditions that this would be a normal model. The mean of that sampling distribution, if you remember back to our sampling distributions problems, mu p hat is equal to p, which is 0.21. So we know that's what's in the middle. And then our standard deviation is square root of p times 1 minus p over n. Again, this is the same as for sampling distributions. So square root of 0.21 times 1 minus 0.21 over 100, just 0.0407. So you can kind of imagine, right, if we go out our 3 standard deviations in either direction, each of those standard deviations is about 0.04, right? And that'll help us find a z-score, right? So we're finding a z-score for our observed value. Our observed value was our sample proportion of 14 out of 100. So 0.14 is our observed proportion, minus the mean was 0.21, divided by our standard deviation, 0.0407, gives us a z-score of about negative 1.72. And we would go look up that in our z-table. So 0.14 is 1.72 standard deviations below the mean, so it's down here somewhere. And then we have to shade. If we're going to find a probability from our z-table or whatever, we're going to have to shade in one direction or the other. So which way do we shade? Well, we shade in the direction of our null or our alternate hypothesis. So since we are trying to test is p less than 0.21, I'm going to shade to the left, just like that. So when I look up in my z-table to find that probability, to find that proportion, I'm going to use the less than proportion. Remember, your z-table always gives you the less than proportion. So if we wanted the greater than proportion, I would need to do 1 minus whatever number. So I look that up in my z-table, and I get a proportion of 0.0427-ish. So again, that probability that our p hat, that our sample proportion is less than 0.14 or 0.14 or less, is equal to 0.0427. So that 0.0427, there's a 4.27% chance that we would get a sample that has 14% red beads or less if there truly were 21% red beads in the entire bowl. We're going to use that number to test our hypothesis. So again, this is essentially the same process we used when we calculated probabilities of sampling distributions in the last unit, but there is a calculator shortcut, and that's what I'm going to show you real quick right now. So if I go in my calculator, I'm going to go to stat and then tests, and then you have a whole bunch of options for tests. What we're doing right now is a one proportion z test. So I need to scroll down to number 5 that says one prop z test. These steps, by the way, are the same no matter what kind of calculator you have, as long as it's a TI. It's going to ask you for a couple of things. Mine's already filled out because I apparently did this before. But P0, that stands for your null hypothesis. I'm going to come over here and kind of show the steps here. So P0 is the value used in your null hypothesis. X represents how many successes you had in your sample. So in this case, how many red beads we had in our sample, which is 14. N is the total sample size, which is 100. And then for that prop part, that's basically telling the calculator what hypothesis you're using. So we were testing that P is less than P0, 0.21. So we're going to do less than. I'm going to go down. You would just go scroll over there and push enter on the correct hypothesis. And then you can either click calculate or draw. If you click calculate, it just gives you a list of things. It tells you what your z-score was, which is what we got. And then it tells us what our proportion is for that problem, what our probability is. So P equals is that probability. It also tells you what P hat, the sample proportion, which is 14 out of 100 or 0.14, and it retells you what N equals. The other thing you can do, like I said, is you can choose draw. And I kind of like draw. It doesn't give you all the same information, but basically it draws a normal model for you and then shades the proportion that we were finding. So that is a quick way to find your z-score and your proportion. We call that probability that we're getting from the z-table, we call that the p-value. And that's really just to differentiate it from, right, P is the true proportion of red beads in the bowl. P hat is the sample proportion of red beads in the bowl. This is a different number. It's a p-value. It's the probability of getting this sample proportion that we got. So it can get a little awkward, so we start calling it something different. We call it the p-value. So again, I do that for this problem. I'm going to get that number. So it's totally fine to use the shortcut. It definitely makes things much faster. It's also going to be a little bit more accurate. Notice that our p-value 0.0428 is slightly different from what we got when we used the z-table, and that's just because the calculator is not rounding anywhere ever. So we're getting a much more exact probability anyway. So it's fine to do it that way, and I'll go through that process again for the next example. But something to note on your paper when you're writing out a hypothesis test, you must include the type of test you ran. So you either write one proportion z-test, or the other way you can indicate which test you're doing is to write out the formula for your z-score, showing all the numbers and where they came from. And that's kind of how AP exam looks at it, is they need kind of indication of what test you're doing, either by formula, which would be the formula for the z-score, or by name of test. So writing one prop z-test or one proportion z-test, something like that. So you need the type of test you ran. You need to write what the z-score equals. So even though you're not using it directly, the calculator is using it, you still need to write z equals negative 1.72, and then write what the p-value is. So p-value or p equals 0.0428, something like that. So those are the three things that need to be included. Otherwise, it's totally fine to use the calculator to find that information. So then our fourth step is to actually write a conclusion. So we're taking that number that we got, that probability, that p-value, and writing a conclusion. So for that, we need what we call a level of significance. So a level of significance is represented by the symbol alpha, or the Greek letter alpha. This is a value that either we set ourselves or more often we're given that number. It basically is setting the kind of limit of how unlikely would an occurrence need to be before we doubt our initial assumptions. So what we just found was that there's a 0.0428, so 4.28% chance of getting the sample proportion we got if the null hypothesis were true. And so our question is 4.28% unlikely? Or is that just kind of like, that could happen just by chance? So that's kind of what we're deciding. So alpha, or level of significance, is basically we're drawing the line in the sand. If something is less likely than this number, then we're saying we're doubting, right? So it can be any proportion value, but the most common values we see used are 0.10 for 10%, 0.05 or 0.01. If we want a test that requires stronger amount of evidence, if we want to be really, really sure that a change occurred, we would use a lower alpha value because that would mean a probability would have to be even smaller for us to doubt our initial assumptions. But if we're not given a level of significance in a problem, we just usually use 0.05. We would just want to make sure and state what we're using for the sake of the problem. So let's actually apply this to our problem. So basically, once we get a p-value and we know what our alpha is, or we've determined what our alpha level of significance is, we're basically comparing the p-value to the alpha. So if the p-value is less than or equal to alpha, that means it's a small probability. That means it's not very likely to happen to get the sample that we got if the null were true. And if that's the case, we might doubt the null is true. So if our p-value is low, if it's less than alpha or equal to alpha, what we say is that we reject the null hypothesis, right? Because again, that means the probability of getting what we got in our sample would have been really unlikely if the null were true. Therefore, we're doubting that the null is true. We're rejecting that null hypothesis, right? And that means that we have evidence that our alternate could be true. The other side of this is that the p-value could be greater than alpha. It's a larger probability. In that case, that means we basically don't really have doubts that the null is true, or our sample doesn't really give us enough doubts because that thing could have been fairly likely to happen. So we're not doubting our null hypothesis. And what we say in that case is that we fail to reject the null hypothesis. And that kind of seems like double negative situation, but we do need to say it that way. In statistics, it's really important to say it that way. Basically, this means that we don't have evidence for our alternate. And again, we never want to say something like we accept the null or this means the null is true. Remember, our hypothesis test is not really testing, do we have evidence that the null is true? We're testing, do we have evidence that the alternate is true? So it's kind of like an innocent until proven guilty, right? If we have a large p-value and we're failing to reject the null, that basically means we don't have evidence to say guilty. So we're saying they're not guilty, right? We're not necessarily saying it's innocent, we're saying it's not guilty. So we want to make sure and say never accept the null hypothesis. We want to say we fail to reject, or we don't have evidence of the alternate. So let's go ahead and apply that to our problem. So our p-value was 0.0428 or 0.0407 if we use the z-table. Either one, as long as I can see your work, it's fine. They did not give us an alpha or a level of significance in this problem, so I'm just going to use 0.05, but I'm going to state that really quickly just so that it's clear what I'm using. So I'm going to say let alpha equal 0.05, and then I'm going to start writing my conclusion. So my conclusion needs to include just a quick comparison of those two values. So I'm going to say since the p-value, which is 0.0428, is less than our alpha of 0.05, So comparison, and then we need to say what that means in terms of our null. So since our p-value is less than alpha, it was unlikely to happen just by chance. So we are doubting our null hypothesis. So if p-value is less than alpha, we reject the null. Then we're going to go on and say in context what that means in terms of our alternate. So if we're rejecting the null, that means, yeah, we do have evidence that our alternate hypothesis is true. So I'm going to write that out in words. We have evidence to suggest that there are less than 21% red beads in the bowl, because that's what our alternate hypothesis said. So again, the important parts of a conclusion, we want to make sure and compare the p-value to alpha, use that comparison to either reject or fail to reject our null. And then we want a sentence that explains what that means in terms of our alternate hypothesis. We either have or don't have evidence to support whatever the alternate hypothesis says. So those are essentially the steps of a hypothesis test. So those 4 things, we wrote our hypothesis statements, we checked our conditions, we calculated and found the probability. We can just do that in our calculator real quick. And then we're going to write a conclusion based on that probability. The other thing that we could be asked to do, and this would be like a separate situation, a separate problem, is that we could be asked to interpret what that p-value means. So that p-value we got, that 0.0428, what does that actually mean? All right, p-value is, again, just telling us, assuming that null hypothesis is true, p-value is the probability of getting what we got in the sample or something even further away. But of course, we want to say that in context. So let's look back at our example, right? Our p-value is 0.0428. We're going to interpret that p-value in context. So basically, assuming there really were 21% red beads in the bowl, assuming that were truly the case, there's a 0.0428 probability that a random sample of 100 beads would have 14 or less red beads. So important parts of this, assuming the null is true, because our probability came from that sampling distribution that had 0.21 in the middle. So that probability came from assuming that there really were 21% red beads in the bowl. There's a 0.0428 probability that we would get sample results like we got, that a random sample of 100 beads would have 14, or something even more extreme or further away. So that's why we did the or less, 14 or less. So 14 or something even less likely to happen or further away. So those are our p-value interpretation. So I'm going to go through and do one more example. The second example is going to look at what happens if our hypothesis is a not equal to hypothesis, when it's a what we call non-directional or two-sided hypothesis. It's basically the same steps, but there are a few slight differences. So I'm going to go through that real quick. So our example 2, according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 0.25. An administrator at a large high school suspects the proportion is different for the students at her school. She selects a random sample of 200 students from the school and finds that 39 of them have a part-time job. So does the sample provide evidence that the proportion of students with a part-time job is different for students at the school? So again, we know what's happening in her sample. What we're trying to do is figure out, is this sample proportion far enough away from that true proportion? Is it so unlikely to happen that we're going to doubt that 0.25 is true? Or is it just fairly likely to happen, just part of random variation, not that big a deal, and we're not doubting? So first step is to write our hypothesis statements. We're going to start by writing what P stands for. So P is the proportion of students at the school who have a part-time job. So then my null would be P equals 0.25, because that's what we assumed to be true. That's what was stated. That's what was claimed. My alternate, I'm testing that it's different. So that's really important to note, that this question is not saying less than or greater than. It's saying different. So that is when we use the not equal to hypothesis for alternate. Again, we could write those hypothesis statements in words. So you could write H0 is the proportion of students in the school who have a part-time job is 0.25. Alternate would be the proportion of students at the school who have a part-time job is not equal to 0.25, something like that. Second step is to write our conditions. So our first condition is that we have a random sample, and it does say that we have a random sample of students from the school, so we were given that. Our second condition is that that our sample is less than 10% of the population. So our sample size of 200, we're going to assume is less than 10% of all the students at the school. In other words, that there are at least 2,000 students at the school. And then our third is checking the NP and Q. Remember, P in our hypothesis test, we are using the null hypothesis 0.25 as P because that is what we are assuming to be true. So NP would be 200 times 0.25, which is 50. And then NQ would be 200 times 0.75, which is 150. Both of those are at least 10, so normality is good. We are allowed to use a normal model to find this probability. Third step would be to do the calculations, right? So again, I'm going to go through the actual math part of it and show you how this is slightly different, and then I'll show you on calculator as well, just to go through that one more time. So our z-score would be our sample proportion, which is 39 out of 200, which is 0.195. I thought I had that up here somewhere, but apparently not. So 0.195 is the 39 out of 200 that we got from our sample, minus our mean, which would be the true proportion of 0.25, divided by our standard deviation, which would come from that formula, square root of p times 1 minus p over n. So square root of 0.25 times 0.75 over 200. And that gives me a z-score of negative 1.796. The p-value I get from that is 0.0724. So let's go back to our calculator and look at how we got that. So again, we do stat, we do tests, then we're going to do number 5, which is 1 proportion z-tests. We're going to put our null hypothesis, which is 0.25. We're going to put our x, which means the number of successes in our sample. So 39 of the sample had a part-time job, so 39. Then it is the total sample size, so 200. And then we were testing not equal to, so I'm going to click that. And then I'm going to go down and I'm actually going to pick draw because I want you guys to see what is happening on the graph when we do a two-sided or not equal to hypothesis, and that's why it's called a two-sided. So here is our normal model. So notice that when we do the not equal to hypothesis, we actually end up shading on both sides of the graph. So the reason for that is a not equal to hypothesis is basically testing for a general difference in either direction. We're not necessarily testing less or greater, we're testing just overall, is it different? So when we find our p-value, the 0.195 is this line right here. 0.25 is in the middle. So 0.195 is this line on the lower end, and we shaded less than that because we wanted something more extreme. And then what we do for our two-sided is we go the same distance away on the other side and shade greater than, because we're testing generally, is it different in either direction? So what ends up happening with our p-value is it's this lower probability multiplied by 2 because we have two sides that we're shading. And that's where the p-value comes from. So if I were to look this up on my z-table, if I were to look up negative 1.8 on my z-table, I would get a smaller p-value, like 0.03 something, and then I would have to double it to get the total p-value. Again, the calculator does all of that for us very nicely and beautifully. If we use that one prop z-test function and put in all the right information, your calculator knows how to get to that number. But just in case you're curious, that's what's kind of happening behind the scenes in a not equal to hypothesis. And we, again, call this a two-sided or non-directional hypothesis. So that is our p-value, 0.0796. Again, in terms of work on one of these on a free response, writing out the z-score equation like I did here would be enough to qualify as, naming the type of test. But you could also just write 1 proportion z-test somewhere up here at the top, and then just make sure to write what the z-score equals, and that would cover your butt as well. So then we're going to go ahead and write our conclusion. Again, we're not given an alpha, a level of significance, so I'm going to use 0.05. And then we compare our p-value to our level of significance. 0.0724 is greater than alpha of 0.05, basically meaning it is not incredibly unlikely to get a sample proportion like the one that we got. So we are not doubting our null hypothesis. That proportion, that p-value, is not low enough to make us doubt our initial assumption. So we are failing to reject the null hypothesis, which means that we don't have evidence of our alternate. We're failing to reject the null. We cannot reject that initial assumption, which means we cannot say that the alternate is true. We do not have evidence that the school's proportion of students with a part-time job is different from 0.25. We'll talk about this more next time and kind of get an idea behind where this comes from. I'll give you some tricks, but that is our first couple of examples.